Picture this. You're in a manufacturing plant. You're standing next to a dangerous piece of equipment. It's powered off, but it doesn't sense that you're close by, so it suddenly restarts. Talk about a bad day. Real-time locating systems aren't just used to find a parked car or a lost item in your home. So security flaws in this technology, especially in industrial environments, can be deadly. I'm Roya Gordon. This is Andrea Palanca and Luca Cremona. We're on the research team at Nozomi Networks, and today we're presenting on ultra-wideband real-time locating systems and how seemingly secure radio communications may fail in practice. This is the first time we will be revealing these 0 days, and we're happy to be doing it on the Black Hat stage. Okay, so what is ultra-wideband, and what does it have to do with real-time locating systems? And for the remainder of the talk, we will be using the terms UWB and RTLS. So ultra-wideband is a radio frequency used to transmit information quickly over short distances and through solid objects. It's preferred for RTLS, which is mostly used indoors where there's lots of barriers. A real-time locating system is a technology that uses signals to locate stationary and mobile objects. If you take a look at the diagram on the screen, you'll see the three main components to this technology. You have the tags that's attached to a person or asset. It transmits location data to the anchors. The anchors submit that data to a server where it does all the processing and the computing, and then displays it in the screenshot. So RTLS is used throughout several industries. It's used in smart cities for management of mass transit. It's used in smart buildings for access control. It's used in smart retail for hands-free payments. I mean, the use cases are endless. So any security flaws in this technology can be pretty widespread. All right, so what motivated us to do this? So in 2020, the IEEE released an updated standard increasing the security of wireless network communications. They added cryptography and random number generation to prevent threat actors from eavesdropping and doing other manipulation tactics on UWB. Great, everything is secure, we can all go home, right? Not quite. Upon further research, we saw that the synchronization and exchange of location data was considered out of scope by the standard, leaving the burden of securing these communications strictly up to the vendors, which can be puzzling, challenging, and even a little intimidating. Upon further review, we saw that there wasn't really much research out there on this specific topic. And so the research was born. And with that being said, I'll pass it over to Luca and Andrea to get into the scope and methodology.
Okay, so during the introduction, we see how ultra-wideband RTLS are a widespread technology that can be deployed in many situations for a large variety of use cases. In the following slides, we will see the scope of our research, both in terms of industrial scope and technical scope. So for our research, we focused on two different sectors, healthcare and industrial. The reason why our choice is twofold. From one side, those sectors were affected by an increasing number of cyber attacks in these last years, while for the other side, those sectors use ultra-wideband RTLS for safety purposes, such as employee and patient tracking. Then for contact tracing, you know that in those last years with COVID, we need a system that is able to raise alert whenever two people get too close to each other. So contact trace is for this. And then geofencing. Geofencing can be seen as a set of rules that can manage the access of people in maybe restricted access areas. So once we defined the industrial scope, we moved on with an analysis of the ultra-wideband RTLS kits that are available in the market. We consider some aspects such as availability, time to delivery, cost, proposed feature. And at the end, we choose these two ultra-wideband kits as representative for the market. The first one is the Sevio Indoor Tracking RTLS ultra-wideband Wi-Fi kit. And the second one is the Avalue Renity Artemis Enterprise Kit. So normally, in ultra-wideband RTLS scenario, there is a tag which is communicating with a set of anchors deployed in specific positions of a room by means of ultra-wideband signals. Those anchors, besides communicating with each other, again, by ultra-wideband signals, are communicating with a central server using standard media technology, such as Ethernet or Wi-Fi. Up to now, security research has exclusively focused on the analysis of ultra-wideband signals. This is the first research that is analyzing the communication on Ethernet or Wi-Fi.
OK, so there are many TDOA algorithms to locate assets in any kind of environment. To better clarify the procedure and understand the preconditions that are necessary for an attack, it is worth doing a brief analysis of the fundamentals. Oh, sorry. OK, so there are two kinds of packets exchanged among anchors on server: synchronization packets and positioning packets. The anchors clocks are usually not in sync with each other for a variety of reasons: clock drifts, different boot times, etc. Thus, a synchronization schema is necessary. One of the most common ones is the wireless synchronization schema. So, periodically, a reference anchor sends an ultra-wideband signal that is received by all other anchors. The reference one sends to the RTLS server the instant at which it has transmitted it inside the synchronization packet. Then a reference ones the instant at which they have received it. The server uses the information to build a common notion of time. Positioning packets, instead, are used for tags localization purposes. As anticipated by Luca, a tag emits an ultra-wideband signal that is received by all anchors. This sent to the server the instant at which they have received it inside positioning packets. OK, so you can see our formulas at the bottom of this slide, but don't be scared. Here we will give you the main concepts. However, for the hardcore geeks, our white paper contains all details. Now, there are many synchronization algorithms in the literature. In this work, we use the linear interpolation algorithm that is a simple yet effective way to achieve synchronization. In a nutshell, the idea is that the RTLS server, at each algorithm iteration and on the basis of the synchronization packet received so far, estimates the clock skews between each known reference anchor and the reference one, and then converts all positioning packets to the global timestamp domain. Those converted timestamps are called global times. We cannot immediately derive the distances from the global times because we are missing a transmission instance. The tag doesn't send this information to the RTLS server. What we can do, though, is to correlate the difference of global times with the difference of distances. This is exactly why this algorithm is called time difference of arrival. Finally, by putting together all equations, this is the final linear system of equations that allows to get the position of the tag. As you can see from the system, in order to obtain the position of the tag, we need three pieces of information: all coordinates of the anchors involved, the synchronization timestamps, and the positioning timestamps.
OK, so after studying the background and the theory about TDOA algorithms, we move on with a reverse engineering activity in order to understand the TDOA procedures that are executed by the anchor and the server, in order to be able to dissect all the traffic, understand how the network traffic is processed. And then we did also some security checks on this system. These slides show a Wireshark screenshot taken while analyzing the Savio network traffic. As you can see, Savio ultra-wideband kit, but also the Avalio one, use a custom unknown binary network protocol for the communication between the anchors and the server. No common data structure can be found, so a reversing engineering activity was needed in order to be able to dissect all the traffic. So we started from the source code you can find on the left of the RTLS server for both Savio and Avalio ultra-wideband kits. We were able to completely dissect the traffic by analyzing the source code, and then we formalized all our activity in two Wireshark dissectors that can be downloaded from the briefing page of this session or from the GitHub page of our company. While performing the reversing engineering activity, we also focused on some security aspect about the communication from the anchors to the server. We mainly focused on two aspects, which are confidentiality and integrity of the data. And guess what? Both Savio and the Value Ultra-Wideband Kit are not able to guarantee either data confidentiality or data integrity. So for what concerns data confidentiality, as you can see from the top right picture, all the location timestamp and the synchronization timestamp are sent in clear. So no confidentiality can be guaranteed. For what concerns data integrity, both the ultra-wideband kits use a non-secure integrity mechanism. For example, Savio uses a CRC16 checksum, while Avalue, as you can see from the bottom right picture, use a byte-wise sum of all packets as a checksum.
OK, so in the previous section, we were able to conclude that there is neither confidentiality nor integrity protecting the timestamps. However, in order to get the position of the tag, we still need the anchor's coordinates. According to the test done, the anchor's coordinates are manually input at the first installation of an RTLS and then never transmitted again through the network. This turned out to be the most challenging requirement for an attacker and can make a difference in the ultimate ability of estimating the position of a tag or not. If the attacker has physical access to the monitored area, this problem can be solved in a variety of ways. If the anchors are visible, it is trivial. If the anchors are not visible, an attacker can still estimate their location, for instance, by measuring the power level of their transmitted wireless signals, be them ultra-wideband, Wi-Fi, or other. As a matter of fact, according to the test done, the anchor's coordinates do not need to be super precise in order to get the position of a tag. This chart that you can see on this slide correlates the average error of the tag coordinates while varying the error of the anchor's coordinates used as input. As you can see from this chart, if the anchor's coordinates are estimated with an error that is less than 10% or about 10%, the resulting tag position is going to be estimated with an error that is less than 20%, but this is about 50 centimeters in a 6x5 meter room, and is definitely enough to perform attacks where centimeter level precision is not really required. However, what if the attacker is remote? As a matter of fact, this information is never transmitted through the network. Nevertheless, there is a technique that remote attackers can apply that we devised and we are presenting to you right now. So, together with the timestamps, anchors transmit to the RTLS server also the power level information of the received ultra-wideband signal. This allows the RTLS server to filter out poorly received communications. With this information, the RTLS server computes two different metrics: the first pass power level, that is the power level just for the first pass signal, and the received power level, that is the overall power level of the ultra-wideband signal. Unfortunately, we cannot derive immediately the distances from the power level information because those wouldn't be precise enough. As a matter of fact, they are too dependent on the environmental conditions that exist in a given moment. However, if in a given moment the power level information that comes from all anchors is almost identical, the tag that emitted these ultra-wideband signals can be considered about exactly the same distance from all of them. But if this is true, the first equation goes to 0. And remembering that, by definition, the clock skew of the reference anchor with respect to itself is 1, and the time of flight of the reference anchor with respect to itself is 0, an attacker can now have enough information to estimate all time of flights between each non-reference anchor and the reference one, and thus their distances. OK, but having the distances is still not enough. We need the coordinates. To this extent, an attacker can leverage an installation constraint of RTLS. As a matter of fact, thanks to the dilution of precision phenomena that correlates the position error with the anchor's geometry, RTLS vendors require that anchors are deployed in a shape that is as regular as possible. Ideally, it must be a square, at most a rectangle. However, given that we know the distances, and given that now we know that the anchor's map is going to be as regular as possible and most times a rectangle, by arbitrarily selecting the reference anchor in position 0, 0, the coordinates of all other anchors can be easily estimated because they will be given simply by the two shortest distances. And of course, an attacker can adapt the estimated shape on the basis of the number of anchors detected in the communications. This was actually tested in the Value RTLS by monitoring a moving tag for about 2 hours. Notably, this chart that is depicted in the slide correlates the average error of the anchor's coordinates while varying the acceptance threshold at the first power level. This chart means that if we set acceptance threshold the first power level to 1%, the anchor's coordinates are going to be estimated with an error that is less than 10%. But if we remember from the previous chart, this translates to an overall error of the tag position. It is less than 20%, and thus those 50 centimeters that I was previously mentioning. But this means, overall, that a completely remote attacker can have an estimation of the anchor's coordinates, and thus can have an estimation of the tag position, and thus practically mount attacks against this system. Which attacks, I will let Luca explain you all.
OK, so in the previous slides, we saw how to get the tag position starting from the timestamp that are sent from the anchors to the server. In these slides, we will see the adversary tactics, techniques, and procedures. That is the behavior of an attacker that wants to do an attack to those kind of kits. So to perform any meaningful attacks against RTLS, an attacker first needs to intercept all the network packets. To do this, first of all, he needs to get a foothold on the network that is used for the communication between the anchors and the server. And then, if needed, he needs to execute a man-in-the-middle attack in order to fetch all the packets. So both Savio and Avalio ultra-wideband kits allows Ethernet or Wi-Fi to access to the network backhaul. In case of Ethernet, in order to access the network, an attacker either needs to compromise a computer which is inside the network, or add a rogue device that will act as a network tap. The complexity of those kind of attacks depends on the network topology and, more precisely, on how the anchors are deployed within the networks. For example, if the anchors are deployed in more than one subnetworks, for an attacker, it is sufficient to gain a foothold on one subnet in order to be able to see all the traffic. So, for what concerns Wi-Fi, both the ultra-wideband kit we examined support WPA2 PSK as a protocol for secure the network communication. So this time, to gain access to a Wi-Fi, an attacker needs to either know the WPA2 PSK password or exploit some vulnerabilities, if any, in a network appliance which is inside the network where we want to do the attack. As for the first point, out of the box, both the solution provide a custom, a default password, which is publicly available on the documentation which is on the internet, and everyone can access it. So the asset owner, the final asset owner, if is not going to change this default password on his kit, for an attacker it is trivial to access this network. So, as I told you before, as a second step, an attacker may need to perform a man-in-the-middle attack. In these slides, we show the output of our man-in-the-middle attack and the screenshot from Wireshark showing that once the man-in-the-middle attack is launched, we are able to see all the network traffic from the anchors to the server and vice versa. It is important noticing that for both the kit we analyzed, it was sufficient to execute a standard ARP attack to be able to execute a man-in-the-middle attack. And also, it is worth noticing that the attacks were completely undetected by the RTLS, and no warnings or abnormal behavior that may alert an operator were shown. So, at this point, we launch the man-in-the-middle attack, we get access to the network, then we are ready to start fetching the position of the tags. So, picture number one shows a possible position of a tag in a certain environment. Then we need to intercept all the traffic, and now we know how to do it. And then we need to apply a standard time difference of arrival algorithm that are available in literature to be able to compute the position of the tag, which is shown in picture number 4, in our own application or environment. At this point, a logic question is, it is possible to perform an active traffic manipulation attack? Well, the answer is yes, of course. To do this, an attacker needs to perform a two-step procedure. From the first step, he needs to perform a target reconnaissance and mimicking. The aim of this step is to monitor the normal behavior and the normal movement of the tag within the environment it is in order to be able to replicate this behavior. And so a possible monitoring system is not able to detect some abnormal behavior of this tag. The second step consists in an active traffic filtering. The key idea for this step is to leave the traffic as it is, as far as possible. So all the synchronization packets and the location packets that are that refers to tag we are not interested in needs to be directly forwarded to the destination, while location packets that are referring to the tag we are interested in attacking needs to be changed, modified, change the payload, change the timestamp, and then sent to the destination. For this work and for our demos, we leverage NFQ, which is a flexible user space packet handler provided by IP tables. And the key idea behind the NFQ is to store all the packets in a temporary queue, then so that we can process one by one, and then we can send the modified packet to the destination. So now we know everything. The last thing we need to do before really be able to perform an attack is to really modify the packet content. So to do this, you can notice in this slide that the four bottom pictures are the same one as for the passive eavesdropping attack we showed before, but in the reverse order. The reason why is that in the previous case, we started from the network timestamp to reach the tag position. In this case, we start from a certain tag position, which is the one we need, we want that the tag is, or the tag will appear to the operator, and to obtain the timestamp that makes this tag be in that position. Okay, so this time we choose a certain position, like in picture number 1, that we apply the TDOA algorithm in backwards, so that we can compute and we can get the timestamp we need for a certain position of the tag. We need to recompute all the checksum, reapply the checksum, and then we can send the packet to the destination.
All right. It's demo time. So we're going to demonstrate how an attacker can exploit the vulnerabilities we discovered in 3 attack scenarios. So our first scenario is locating and targeting people and assets. We show how a threat actor eavesdrops on the network traffic in order to locate and target an asset. Why would they want to do this? They could want to stalk someone. They could want to locate and steal something, or they could just simply want to learn the environment. Let's take a look. This is our victim in the first video wearing the tag. So we're first going to see how tag tracking works as normal. So Andrea's been working all day, sitting at his desk. He wants to stretch his legs, so he's taking a stroll around the office. Beautiful day in Switzerland. Now, because he's wearing the tag, the RTLS server shows his movement. And as you can see, everything is accurate, all is normal. Now let's see how a threat actor can manipulate this to eavesdrop on the network traffic. So on the left is a Wireshark packet capture. It shows that there's no location data populated. Therefore, the red dot that's up at the right, it doesn't move. But once the man-in-the-middle attack is launched, all of that location data is loaded, and now we start to see the red dot moving. So this is what the attacker is able to see. Now let's compare it with the actual RTLS server. So on the right, you have the attacker view, which is identical to the actual RTLS view. What's most concerning about this is that there's not even an alert generated of this compromise. So this is what eavesdropping on an RTLS server looks like. Okay. So in our second attack scenario, we show how a threat actor can manipulate an RTLS server that's used for contact tracing, like in COVID-19. And for the purpose of this, no one has COVID, but for the purpose of the demo, someone has COVID, so we can show what it looks like to fake contact or to be in contact with someone who has COVID, but it looks like you weren't in contact. Don't worry, we'll explain it in the demo. Okay, we have the two victims in the demo here wearing the tag. Now we're going to show you how contact tracing works as normal. Okay, they're both wearing the tags. You see they come into contact with each other, and an alert is generated showing that there was a COVID encounter. So let's see how a threat actor can manipulate this to fake contact. Andrea just walks past Luca. No hi, no nothing. Now, when the attacker launches the attack, it shows that they, in fact, came in contact with each other, which is not accurate. And then an alert is generated to show that someone came in contact with COVID, again, which is not accurate. Now let's see how an attacker can manipulate this to fake avoidance. Andrea's feeling more social today. Now, when the attack is launched, the threat actor is able to manipulate the positions to show that they didn't even come in contact with each other. And because of this, there's no alert to show that someone came in contact with COVID. And we know how damaging that could be. So our last and final demo is geofencing. So we configured a SCADA system from our production line demo in our lab to listen to RTLS geofencing alerts to control a motor in two ways, to either start or stop, depending on if a worker is inside or outside of the geofencing zone. Let's take a look at what this looks like. Here's our victim in this demo wearing the tag. Now, this is our production line demo in our lab. It shows the motor rotating the flasks, and then there's a machine that's scanning the barcodes. Now, here's how safety geofencing works as normal. So you have the worker approaching the production line. Everything shuts down because he's within the geofencing zone. However, when he leaves, production resumes as normal because he's outside of that safety zone. And you can see it in the RTLS server here. The tag is within the geofencing zone. An alert is generated to shut down production. And then when the worker is outside of that zone, there's another alert generated to resume the production line. Now let's see how a threat actor can manipulate this to stop a production. So as you can see, no one is around the production line. All of a sudden, there's an alert and production stops. Let's see how an attacker did this. So they launched an attack, and they manipulated a tag and put it inside of the geofencing zone. Because of this, it generated an alert, and it shut down production. But as you can see, there's no one around the production line, and all is safe. Now let's see how a threat actor can do this to restart a production line with workers nearby. Okay, so we have our worker at the production line. The warning light comes on. Everything stops as normal. But when the attack is launched, the threat actor is able to manipulate that tag and take it outside of the geofencing zone. And because of that, production now restarts, putting the worker in harm's way. Just imagine this happening in a manufacturing plant and the harm that it could do to workers. This concludes our demos. Thank you.
OK. So having shown what an attacker can do against this system, it is now worth mentioning what are the possible mitigations that an asset owner can apply. The first logical mitigation is to move the RTLS into a segregated network and secure its access both physically and logically. This is now mandated by some RTLS vendors. The advantages of this solution is that it is relatively quick to deploy and can be enacted basically using very traditional network security solutions. However, some challenges need to be considered. First things first, the RTLS server usually has two network interfaces, one attached to the backhaul network, the other attached to the management network from which operators connect. If those core network, also, by default, most RTLS services tend to expose core network security services on all interfaces by default for simplicity reasons. So if those core network services are not adequately filtered from the management network, there could be room for denial of service attacks. An attacker wouldn't be able to enact the attacks that we have shown so far because it is missing vital information. However, by fuzzing packets against those core network security services, it might actually be able to block the update of tag position and thus tamper with geofencing and the contact tracing rules that we had just shown. Additionally, if an attacker managed to physically attach to the wire or compromise the wallet password, at that point there would be nothing preventing them from successfully enacting all attacks shown so far. The second mitigation is to add an intrusion detection system to the backhaul network. As a matter of fact, as an attacker is bound to do a man-in-the-middle attack by monitoring for signatures such as new links between nodes, any intrusion detection system available on the market can perform these kinds of attacks. The advantage is that it is very quick to deploy and it's pretty much plug and play. However, again, it is inherently vulnerable to a physical man-in-the-middle. As a matter of fact, even in the worst case, the active traffic manipulation attack, the crafted traffic would be undistinguishable from the legitimate traffic if it precisely mimics the natural movements of a target. Ultimately, the main problem is the lack of transport protection measures. Thus, the most effective mitigation that an asset owner can apply is to add an encryption and integrity layer on top of the existing communications. As a proof of concept, and with the goal of using already well-known tools, we attempted to add as an SSH tunnel on top of the value RTLS. As you can see from this slide, the POC result is successful. We were able to encrypt all traffic while preserving the RTLS functionalities. However, again, some challenges need to be considered. The SSH tunnel increased the load on the anchors and, in the end, added noticeable delays. We were able to counteract this effect by decreasing the synchronization frequency, but this also reduced the accuracy. And this might be a problem for asset owners that want real-time precise tag position. Additionally, this entire mitigation depends on the accessibility of either the RTLS server or the anchors by the vendor. If one of them does not allow admin access, enacting this solution either requires an extensive work of firmware modification or would be simply not viable. And with that said, I will leave to Roya for the conclusions.
All right. We unpacked a lot, so let's do a quick recap. Security standards don't cover everything, but with RTLS being widely used, we can't afford to have those loopholes in standards. We disclose zero-day vulnerabilities in two popular UWB RTLSs. They're used for personnel tracking, geofencing, and contact tracing. And we even demonstrated how a threat actor could launch a man-in-the-middle attack to eavesdrop or do other manipulation tactics. We also provided some mitigations. Now, if you don't remember anything else during this presentation, we want you to walk away with these three things. Number one, weak security requirements in critical software can lead to safety issues that cannot be ignored. Safety-critical software should have well-defined security standards, period. Number two, there are attack surfaces out there that no one is looking at, but they have significant consequences if compromised. So while everyone was focusing on the communications between the anchors and the tags, no one was focusing on the communications between the anchor and the servers. So it's important to look at the entire attack surface and not just focus on one part while ignoring others. And last, exploiting secondary communications in UWB RTLS can be challenging, but it's doable. Now, prior to this talk, these attack scenarios were considered unlikely, but clearly in this presentation, we showed that even though it does require specific knowledge, it can be done, and the devastating effects it can cause. At the end of the day, you can't have safety without security. We hope this talk not only made you aware of security flaws, but motivated you as researchers to continue to find those vulnerabilities to safeguard individuals, businesses, and the world. Security can be puzzling, challenging, and maybe even a little intimidating, but it can be done. Thank you.